We are going to continue to work on inverses, and then we're also going to learn how to check to see if functions are inverses and then do what's called composites. But before we do that, why don't we go ahead and write the equation for both of these inverse functions. It is up to you how you would like to do it. So I had you already complete them both ways, writing out the steps and then inverting the operation in the reverse order, or interchanging x and y and solve. It does not matter to me at all how you do it. It will be completely up to you. You just need to make sure that you're good at whichever way it is. But these two warm-up questions are the two odd situations, one where there's a square where it starts as a parabola, and the other one where there's a square root. So go ahead and pause this, write both of the inverse equations, and then unpause it, and I'll give you the solutions to them. So I prefer to just write out the operations and then invert those. So therefore, the first thing I'm going to do is subtract the 4. And then I'm going to divide all that by 2. And then I'm going to square root it. And as soon as I square root it, it's the positive and negative. And then it's minus 3. It's plus 3. And you can either write the 3 at the end or write the 3 in the beginning. So then it would be 3 plus and minus that. And again, I'd have 2 of those equations in there. So this one started out as a parabola. If I only did the positive one, I'd only get the halfway sideways parabola. So now with the negative, I get the bottom of the sideways parabola. And again, you can always check that in your calculator if it was on a calculator assessment. The second one is a square root function. So this looks like this. So hopefully that makes you start to think, hey, I have a square root function, so when I do the inverse and I get a quadratic, that's too much information. So now we're going to go ahead and write out the operation. And so when I do my inverse, the first thing I do to my x value is subtract the 3. Then I divide all that by 2. Then I'm going to square the whole thing. And then I'm going to subtract 5. So now I have to limit my x value. So we always limit our domain. So if I look at my original function, this starting point shifted 5 units to the left and 3 units up. So therefore my domain is x is greater than or equal to negative 5. My range is y is greater than or equal to 3. Therefore my domain is x is greater than or equal to 3. The interchange x and y, so my domain becomes my range becomes my domain. Please be careful if there are any kind of reflections, because maybe this graph ends up going like, maybe the graph ends up going this way, or like this, or something like that, just based on where its reflections are, so double check those multipliers as well. So now we're going to move into composite functions. And composite functions, we're going to be joining multiple functions together. So composite, combining. So here is a story problem. I'm going to have you pause it to read it because I'm not going to read through everything. But what I want you to do is I want you to be able to start going through the process. Now, one of the things that we're looking at are a pair of the equations that we had done in the previous video. So we're going to be looking at these equations here. So we're going to be looking at using just A. So what I'm going to do is I'm just going to write these in here. One of them is going to be f of x, one of them is going to be g of x. So since we're starting with f of x, we're just going to say let f of x equal 2 times the quantity of x minus 1 cubed. And then g of x, its inverse, is the other one, and that's the cubed root of x over 2 plus 1. So those are the two functions that we're going to be using with this function machine. So again, pause it, work through the questions here, and then I'll talk through a few pieces with it. Okay, so we're going to put 3 into my f of x equation. So therefore, this ends up being, it's not going to be the cleanest, but here, let's see, 2 times 3 minus 1, that's a 3 minus 1, and then that's the third part, because our input was 3. So when I put that all in, 3 minus 1 is 2, 2 cubed is 8, times 2 is 16. So 16 is my output. Then what it's saying is 16 was the output of f of x. So that's now my input into g of x. So now I put 16 into my g of x equation. So that ends up being, I'm going to do the work over here, the cubed root of 16 over 2 plus 1. So 16 over 2 is 8, cubed root of 8 is 2, 2 plus 1 is 3. I get an output of 3. So when I put in 3 in, I got 16 as my output. 16 became my new input into this function, and my output became 3. It's the same thing. Pretty handy, huh? Notation-wise is important because we're putting in f of 3. Therefore, understanding what you're going to get out each time is with notation, this is the part that I want to focus on. So this is the notation that we have. G of f of 3 is 3. So I put 3 into my f function first, so that's what this part is right here. That's 16. So then G of f of 3 is technically an output. My output was 16. But 16, that was the output, becomes the input, because it usually says G of x. Now it says G of 16. So 16 becomes the new input, which is 3. So being able to read these is going to be really important. And order matters, because in part C, it says, hey, what about writing it as f of G of 3? And that's how you state it, f of G of 3, which means 3 goes in for your G function first. So that means I need to put 3 in here. And then I get that result, and whatever that result is, that goes in there. And order is different. I'm going to do different operations to it. So you have to be careful and make sure that you're putting it into the correct function in the correct order. So therefore, if I wanted to put this in for any different situation, I will end up getting that whatever this input was. Because these are inverses of each other, I will get that final output. Okay, so now we're going to look at more composite notation. So instead of putting in 3 and putting in 7 and putting in 10 and putting in 15, what we want to be able to do is combine these two functions together as one. So if I combine these two functions together as one, I won't have to do all of this work. Now again, I'm looking at doing this with two functions that are inverses, but I can also do f of g of 3 into two functions that are not inverses. And how this comes up and how it's helpful is, say I'm driving a car. And if I'm driving the car, the speed I'm going depends upon the temperature that we have outside, how my tires are grabbing onto the road. Is it snowy? Am I going up a hill? What pressure am I putting on it? So we have a bunch of different functions that are all affecting what the speed of my car is actually going. So in order to take that into consideration, we'll be doing composites of functions. And again, they're not always inverses. We're just doing this with inverses because there's some nice features that happen. So what he's talking about here is if I use that strategy, but instead of putting in a number, so instead of doing g of f of 3, I skip that and just put x in, and I do g of f of x. Will I still be able to show that we have inverses? So if I put a 3 in and I get a 3 out, hey, those look like inverses, because what I put in, I get that back out. If I put a 7 in and I get a 7 back out, they should be inverses. Not always perfect, but what if I just worked with x? Okay, so I can't try an infinite number of values, so instead, let's put that generic x in. So if I put x in, what should my output be? My final output should be x. Because my original input here is x, my output, if they are inverses, should also be x. And that's how we can prove they're inverses. So that's what we're going to do, and we're going to combine g of f of x using these same two functions. So g of, in my f function, in place of x, normally it would be f of 3, I'd put 3 in for x, but it's not, it's f of x, so in place of x goes x. So really, I'm just writing that function out. Yes, my input is x, but this is what I get. That's my function. I replace f of x with my function, because that's what I get when I put x in. So now, that is the new input. So this here is the new input into my g equation. So now, instead of g of x, it's g of that input. So wherever there's an x, that mess goes in place of it. So, let's get my pen back. This is equivalent to the cubed root of x. X is 2 times the quantity of x minus 1 cubed. But that's still divided by 2. And then it still says plus 1. So now what I'm going to have to do is simplify that. So simplifying the process, 2 over 2, that simplifies. And this gives me the cubed root of the quantity of x minus 1 cubed plus 1. And the cube root and the cube undo each other. Therefore, you get x minus 1, and then you still say plus 1. Well, those undo each other, and you get x. So when my original input was x, my final output was x as well. Therefore, they're inverses of each other. You've just proved that they are inverses of each other. So, does it show that the two equations are inverses? Absolutely, because when I put in that generic input of x, my final output was also x. I'm going to have you practice doing this as well on your own, but before that, I just want to talk quickly about the following. So Trejo says that if you know the x-intercepts, y-intercepts, domain, and range of a function, that you automatically know the x-intercepts, y-intercepts, domain, and range for the inverse. Hillary disagrees. She says you know the intercepts, but that's all you know for sure. Who's correct? So hopefully you remember when we started talking about restricting our domain, our input values, we talked about, well, we know that our x values and y values switch. So my x-intercepts become my y-intercepts. My y-intercepts become my x-intercepts. My domain becomes my range. My range becomes my domain. So as long as you know all four of those pieces, you then can tell all four of those for the inverse as well. So Trejo is correct on that. Okay, so the last part for this lesson is being able to practice this and doing f of g of x. Please note, if they are inverses, it doesn't matter which one is your original function and which one is your inverse. It doesn't matter if you do f of g of x or g of f of x. It does matter when they're not inverses. But if they're inverses, when you put an x in, you're going to get an x out. It doesn't matter which one you start with. But if they're not inverses, if you put an x in, you're not going to get an x out if they're not inverses. And you're going to get two different output functions. So please keep that in mind, especially because one of these, they are not inverses of each other. So for all three of these, for the first one, just for consistency's sake, so when you check my work, we have them in the same order. Oops. I'm going to have you do f, come on, f of g of x for the first one. And let's also do that for the second one. And for the third one, let's do e of d of x. Again, just important for our notation for our numbers, because the one that is not a function will end up giving us a different output function in the end. And sometimes it might make it easier to do g of f of x instead of f of g of x, just based on how the problem is set up. So it just kind of depends upon what your comfort level is. If you're struggling simplifying it, then maybe go ahead and do the opposite order, because if they are inverses, you should get x out anyways. So take a moment, please, and do composite functions with these. Okay, so I substituted in my g of x function, so now into my f of x. F of x says 3/5, and then there's that x. So in place of x goes 5/3 x plus 25. And then it also says, let's see, f of x minus 15. Okay, so I just rewrote f of x, but instead of x, I put my input in, which was 5/3 x plus 25. So now I have to just simplify this, and I'm going to have to expand the 3/5 through. So what ends up happening is I get an x plus, and then 1/5 of 25 is 5, so that's plus 15, and then it says minus 15, so then that simplifies to x. Perfect. Those are inverses of each other. Okay, so for this one, I put in my g of x function. So now I go back up to my f of x function. It says 2 times, and then it says x. It's kind of ugly because we're going to have fractions and fractions, but still totally doable. 3/2 x minus 21 goes in for that x. And then it says plus 6. And that's all divided by 3. And then it's plus 10. So again, I just rewrote my f function, but instead of my x value, I put in my 3x minus 21. Okay, so now simplify it. Send the 2 through, across. I guess I could have simplified. But so I get x at minus 42 plus 12. That's all over 3 plus 10, which simplifies to x minus 30 all over 3 plus 10. But I lost this 3 here. Sorry about that. So I lost that 3 along the way. That's a 3x. Like something wasn't simplifying right. That was a 3x. Sorry about that. Okay, so I'm dividing that all by 3. So therefore, that's x minus 10 plus 10, which is x. So yes, those are inverses as well. Last one. So therefore, when I plug in for x, it starts right away with the x. So therefore, 4 times the square root of x plus 10. And then it says minus 10. And then that whole thing is squared. And then that whole thing is divided by 4. Okay, so then just simplifying this, we have 4 times the square root of x. That whole thing is squared, and that's divided by 4. Because 10 and negative 10 go away. Okay, so then I have to square the whole thing. Keep in mind you are squaring multiplication, which means you're sending through that squared, or think of it as 4 times the square root of x times 4 times the square root of x, which is 16 times x, because the square root of x times the square root of x is x, over 4, which means this simplifies to 4x, which means they are not inverses. Therefore, if f of g of x is equivalent to g of f of x, and that equals x, f of x and g of x are inverses. If f of g of 2 equals 2, they might be inverses, but it's not a guarantee.